In this video, we're going to start talking about linear regression. And as an example, we're going to use some data, some length measurements to figure out a function that relates pressure in the heart with respect to some certain length measurements. The data we're going to be using for this example have to do with measuring a particular distance together with pressure, and the distance in this case can be obtained by figuring out how long in terms of time or in seconds it takes for a sound wave to go from point A to point B. This can be done continuously as a function of time, as well as can be synchronized with the pressure measurement. So here is the example, or here's actually the data that can be obtained from such a setup. Here you have on one axis you have the segment length in millimeters, right, which is obtained again from that time distance, and the pressure measurement, right? So we can obtain these measurements here corresponding to and with the corresponding pressure measurements. And one of the questions or one of the functions that we would like to obtain here is again the segment length as an independent variable and the pressure as a dependent variable. But of course the heart is alive and it's kept alive, so we would like to understand what this distance is when essentially when there is zero pressure throughout the heart. What would be the dimension of that particular distance? Of course, the heart in this case is alive, so we'd like to continue that to be the case. And so we don't have this measurement at zero pressure, but we can infer what would be the zero pressure if we can fit a line through all this data point, and then we just ask when does the line, at what value for the independent variable does the line cross when the pressure is zero. So what are we going to do here? We're going to come up with a model for a line, and this model we have two parameters. We'll call this A and B, and A parameter will be the slope of the line, and B will be the intercept at the value 0, and up here the independent variable is labeled as P. So how do we fit this line? First, we define an error function between, let's say, we fixed parameters A and B and look at this line as a function of the independent variable P. So we have this line, and for each P indexed here by coordinate by subscript I, we can measure how far the line is from the actual measurements. So we call the measurement data D and the line L, and we subtract the line from the data for the corresponding coordinates, and we sum up the square errors. And we simply then try to find the parameters A and B that make this line pass closest through all the points. In this example here we have this blue line, and you can see all the distance from the line to their particular points. This is not a particularly good fit because you can see this line passes kind of far away from each point. And there will be another much better line that we could use. For example, if the line had a little bit of slope here and was adjusted so that it passes better through this point, you can try to understand that the errors between the line and the points would be much smaller. So how do we do this? And we're going to cover in subsequent videos, but the general strategy is to minimize this error function, right? So we can write this as a function of Q of parameters A and B, right? You sum all of the errors between the line and your data, and as you change the parameters A and B, this error can become bigger or it can be smaller. So we'd like again this is a function of two variables, right? So a two-dimensional function. We would like to find parameters A and B that make this Q function the smallest as possible. What's the general strategy as you learned from calculus in multiple variables? The strategy is to take the partial derivative of q with respect to variable a and variable b and set those partial derivatives to 0. Once you do that, in particular for this linear model here, which we'll also talk about in a second in a subsequent video, if we set these partial derivatives to 0, we then have a function of a and b, which is a linear system of equations. And here we have, in fact, two equations and two unknowns. The two equations here are equation 1, equation 2, and the unknowns are a and b. And if you simply use then Gaussian elimination, for example, in this linear system, you can come back with the parameters a and b that give you the best fit to this data. And here is the best fit explained. Right? And once we have this line, we can then set the intercept to 0 and solve for what is the independent variable so that the pressure is 0, right? What's the segment length that makes this pressure to be 0? You could also have done it by brute force, essentially inquiring for all possible values of a and b, and essentially selecting, computing all possible combinations, and then selecting the one that is smallest. And we'll look at iterative minimization methods a little bit later on.